Okay, so in today's topology seminar, it's a great pleasure to have Osman Berat Okutan from Florida State University, and he's going to tell us about persistent homology and injectivity. So Osman, whenever you're ready.
Okay, I'm ready. Thank you. Thanks a lot for the invitation. It is good to be back at BilTop. Thanks for giving a talk. Okay, so the title of my talk is Persistent Homology and Injectivity, and this is joint work with Facundo Memoli and Sunhyuk. Okay, so let me first mention the general structure of the talk. So first, I'm going to introduce what is the purpose of persistence from my point of view. Okay, so, and then after that, we are going to see two ways of getting persistence from a space, which is given by Vietoris-Rips filtration, and one more using injective metric spaces. And we are going to see a relation between those two ways of getting persistence out of a space. And in the final part of the talk, we are going to see some applications of those relations. And if you have any questions with the talk, please don't hesitate to ask. Okay, so what are we trying to do with persistence or with topological data analysis in general? So a question we can ask is, if we get a finite sample from a space, can we somehow recover topological information from it? So in this example, we have this H shape, okay? And then we are taking finite sample out of it and asking if we can recover any topology from that. And if the only structure on X on the space we have is topology, and assuming it is Hausdorff, then finite sample loses all topology. It becomes discrete, and we cannot see anything from it. Okay, but so what additional structures we can put on X so that we may be able to recover some topology, even if the sampling is finite? So one thing we can do is embedding our space into a metric space. Okay, so now I'm embedding that shape, H shape, into R2, and I'm sampling afterwards. And to make the situation worse, sampling can be noisy. Okay, so it doesn't always have to come from the original space, it can come from outside, or our measurements can be wrong. Okay, so the picture will look like this. And now we have a method. Not everything is lost. Although the sampling doesn't contain any topology, we can look at its neighborhoods, and there maybe we can recover some topology of the original space. And here I am taking a certain neighborhood of that sampling. Okay, so I will denote it by BR. So it is a generalization of an open ball of a single point. Now we can have the open neighborhood, R neighborhood of any subset of a metric space. The idea is you just look at the points whose distance to your sampling space is less than R, or it is the union of R balls whose centers are in your sample space. And as you can see, for this neighborhood, R equals 0.2, we have homotopy equivalence between the original space and the neighborhood space. Okay, so we can recover up to homotopy. We can recover the space if we apply this method for this specific instance. Okay, but one thing important in this situation is choosing the neighborhood carefully. If we choose a too small neighborhood, just like here, okay, I applied a very small neighborhood to that sampling, then again, the situation is not much different from the discrete sample. Okay, still no topology recovered here. And also, if we choose R too big, just like here, we end up with a contractible space, and again, whose own topology does not carry any information. Okay, so we have to choose our neighborhood carefully. How are we going to do that? One way we handle this problem is using persistence for choosing this neighborhood. And what is the persistent answer for choosing R? The answer is do not choose R. What are we going to do? Instead of choosing a specific R, just look at all possible R's or R's in certain region. So get growing and growing neighborhoods of your space, your sample space. Okay. And then look at how topology changes. If you do that, you're going to see that some topological features will appear and die, and others will persist. Okay, so let us look at this one. For example, at this scale, we can see that this feature, a loop is born, okay? And it will live for a long while up until we start to fill everything again. Okay, so this loop is born at very early in our growing neighborhoods, and it will live for a while. And another thing is sometimes because of the nature of the sampling, you can get additional topological properties like this. If you see, there's a little loop here, which is not part of the original space. But the nice thing about persistence is after we increase our neighborhood a little, it will die. Okay, it will become contractible. So we will not see that loop again. And also you can see that this second loop is about to be born. It is not born in this picture yet because there's this little hole, but after a while it will born and persist for a long time. Okay, so what persistence does is considering these families of spaces and keeping track of how topology changes. If certain topological feature lives for a long time, then we consider it as an essential feature of the space. And for other features which are born and die, which dies quickly, we consider them as noise, okay, coming from the sample. Okay, this is the general idea of persistence. And let us make things now more formal, more algebraic. So we are going to introduce certain terminology. Okay, first of all, a persistent family. Persistent family is a functor from the poset, this poset 0 infinity with classical order structure to topological space, to category of topological spaces. In other words, you should have a family. Okay, so let us use letter T. And for each less than or equal to T, you should have a map, continuous map from XS to XT. And by functoriality, it should satisfy this condition, FTU composed FST is FSU. So this is what that means. So we have this sequence of spaces where we have maps between them, which commutes. Okay. And we already have an example of this. If you take a subspace A of a metric space and look at our neighborhoods, you will get a growing family, which is a filtration. Okay, so it is a growing family of topological spaces. And if you take the structure maps FST, by the way, these maps are called the structure maps of the persistent family. If you use the inclusions as your structure maps, you will get a persistent family. And most of the time, the persistent families which are studied are filtrations. But theoretically, we can take any family as long as the maps commute. And a persistent module is the algebraic version of this. You have a functor from 0 infinity to the vector spaces. Okay, so again, we have VTs for each T. And if S is less than or equal to T, then we have structure maps, which are linear maps now. Such a structure is called persistent module. And what we are going to do is we are going to take a persistent family of spaces, topological spaces, then we are going to apply homology to it with some field coefficients. Most of the time R, but we can apply any field. Okay, so take a persistent family, apply homology to it. Since homology is also a functor, you get a persistent module. And this is the main algebraic structure we are going to use when we are talking about persistence. Oh, this is my mistake. I should write here not module, but persistent homology. This is called the persistent homology of the persistent family. And let us see the persistent homology in a simple case. So let us take our space to be circle, which lives in R2, and let us look at its growing neighborhoods in R2. Okay, so a picture will look like this. So it will be an annulus, and it will grow, and finally it will be full disk. Actually, if you look at this picture, there should be a hole at the center. Okay, there should be a little hole at the center because we are looking at open neighborhoods. So at 1, it is not filled, but almost. There's only a single point is missing. So if you look at the homology of this, at the 0 level, nothing changes. You have a single connected component, and all the time you have single connected components. So at the 0 level, there's no interesting homology. At the 1 level, until we come R equals 1, we have always a single loop. Okay, so the persistent one-dimensional persistent homology will be equal to R. Okay. And the inclusion maps always induce the identity map in the level of homology. And exactly when we hit 1 or just after 1, that loop will die. Okay, so our VTs, when we apply the one-dimensional persistent homology, will be R, the one-dimensional space when T is between 0 and 1, and otherwise it is 0, and the structure maps are identity when it is possible, otherwise 0. And this type of modules will be important, which we are going to mention in next slide. So to complete the algebraic picture, we need to add one more tool, which are the barcodes. Just like we have seen in the previous circle example, circle embedded into R2 example, there are certain type of modules which are important in persistence modules. So those are called interval persistence module. Assume we have an interval J, okay. Then the interval persistent module Vj star is defined like this. Vjt is equal to R, one-dimensional space when T is inside the interval, otherwise 0. And structure maps are, again, identity when it is possible, otherwise 0. And these are the indecomposables of persistence modules, which can be shown. We are not going to show, but which can be shown that this cannot be written as direct sum of more simpler algebraic persistence modules. And it is known that if we put certain tenuous conditions on the persistence module, every persistence module can be written as a direct sum of interval modules. This is the exact analog of having a basis for a vector space. Just like we can write a vector space as a direct sum of one-dimensional vector spaces, we can write any persistence module as a product of direct sum of interval modules. Okay. And when we have a persistent module, V star, and write it as a direct sum of interval modules, the collection of those intervals is called barcode. It is not a set because some interval can repeat. Okay, we can just take the direct sum of these two, for example, which both comes from the same interval. So it is multiset because of that reason. So some intervals can repeat. And that is called the persistent barcode. And then we are handling persistence modules. Persistent barcode are the main things we look for. And there are efficient algorithms for calculating persistent barcode of a persistent module. And similarly, we can define persistent barcode of a persistent family of topological spaces. We are going to denote it by bk x star, which is just take your persistent family, apply kth homology, and look at the barcode. Okay. If we turn back to the previous example, we have seen that at zero homology level, nothing changes. There's a single component which is born at time 0 and leaves up to infinity. So it is this. And for the one-dimensional barcode of this family, there's a single path, single cycle, which is born at time 0 and which dies at time 1. Okay, so this is the one-dimensional barcode of this filtration, this persistent family. Okay, now let us look at our original example. Okay, the example we motivated the discussion. So we have shape 8, we have samples, and we are looking at its neighborhoods. Let us see what happens to the barcode. Okay, let us think with the zero-dimensional barcode, which is easier to see. You just keep track of connected components. So we know that at the beginning, when we start, there will be lots of components. Okay, this is a finite sample. So if this is a finite sample with 10,000 points, then there will be 10,000 components at the beginning. Okay, but after a while, since these points are close to each other and they are coming from a connected space, after a while, we will end up with a single component. And that component will live up to infinity. Okay, it will never die. So we can see that the zero-dimensional barcode of this family is a bunch of very small intervals, then a very big interval from 0 to infinity. Okay, all other one except the final component dies. Okay, now let us see what happens at one-dimensional barcode. Okay, at the beginning, again, there's nothing. After a while, after a short while, we will have two components. Okay, one of them will correspond to two loops. One of them, two cycles. One of them will correspond to this, other one to that. And they will persist for quite a while. Okay, so approximately 0.5 data. So they will persist this amount. So the interval corresponding to those two cycles will be of size approximately 0.5. But we also see that accidentally some loops can form and die. We have seen this in the previous example when we are analyzing this situation more closely. Some accidental loops born, die, but they will be very small. And this is the idea of persistence. If we want, we can ignore those small intervals. And that will be the persistence of this space. And I hope this clears what persistence is trying to do, at least from my point of view. Okay, now let us talk about way to get persistence. Are there other ways? Okay, if you look at what we have done up to now, is the persistence we get is we first embed our space into another space, into a metric space. But this is an extrinsic definition, right? We can use another embedding and may end up with another persistence. So this is not the property of a space itself, but it is just the property of embedding what we are getting. So the question is, if X is itself a metric space, can we get some persistence which is intrinsic to X? There are several ways to do this. The one I'm going to describe is called Vietoris-Rips filtration. Okay. Let us see what Vietoris-Rips filtration is. Okay. Again, I need to introduce some terminology. First, clique complex of a graph. So let us take a combinatorial graph, okay, which means just it's a discrete object, it's not a continuous object. So let us have a combinatorial graph, which means a finite family of vertices and a finite family of edges, which are given as the pair of vertices, or the one-dimensional simplicial complex. Okay, so the clique complex associated with the graph is the maximal simplicial complex whose one skeleton is G. Okay, so what are the simplices of this clique complex? is this: V0 to Vn is a simplex if and only if every pair forms an edge. Okay, so a simplex is inside the clique complex of G if all of its edges are in G. And you can see that this is the maximal. We cannot anything more. And this one skeleton of this clique complex is exactly G. So it is the maximal one. Okay, so if I draw a very simple example here. Okay, so let us take this. Assume this is our graph. To take the clique complex of this, we have to add this face. Okay. Because all of its boundaries are in the graph, but we cannot add any other face or higher dimensional, because for any other simplex, we will be able to find an edge of it which is not contained in our graph. So this is called the clique complex of a graph. Okay, now how are we going to use this? Take your metric space. First, form a graph, okay, whose vertex set is x, the point underlying set of x. And what are the edges? If you are using parameter r, the edges are exactly the pair of points whose distance is less than r. Okay. We are going to see an example of this soon. So form that graph by connecting points whose distance is less than r, then fill the rest, get the clique complex of it. Let us see it in an example. Okay, assume we have this 4-point space. Okay. So we have this 4-point space. How are the distances given? So these are 1, 1, 1, 1. This is 2. This is 2. Okay, assume we have a metric space like this. And let us look at its Vietoris-Rips spaces for different scales. Okay, first of all, there's no distance less than 1. So until we hit 1, we are not going to add any edges, because we cannot connect any two vertices. There's no distance less than 1. Okay, what happens when we just exceed 1? Immediately after we exceed 1, we have to put the edges between this distance 1 vertices. Okay, and nothing more. To add any further things, we have to go to r equals 2. Okay, so add between 1 and 2, our Vietoris-Rips complex will be just S1. It is homomorphic to S1. Okay, and exactly when we come to 2, every edge is there, because there are no distances greater than 2. Okay, so every edge should be added, and now fill this in, you get the full simplex. You get the full simplex, which is homotopy homeomorphic to D3. Okay, not homotopy, but homeomorphic to D3. So it is the full simplex. So in this example, if we look at persistent homology of this, first of all, let us start with 0-dimensional. At first, we have 4 components. Exactly at scale 1, we reduce to 1 component. Okay, so we will have 4 intervals, 3 of them of length 0, 1. And as you see, the intervals can repeat. And last, 1 of them is length infinity. And what happens to 1-dimensional barcode? Up to this moment, we don't have any cycles. Exactly at 1, we will get a cycle, and that cycle will die at 2, scale 2, because we get the full simplex. So it becomes contractible after it. So 1-dimensional barcode is 1 to 2. And as you can already see in this example, this persistence catches the circularity of this metric space. Okay, it was able to catch a 1-dimensional barcode. We are not going to do this now, but if you take 6 points instead, okay, so if you just take 6 points, circular 6 points, calculate the persistent homology, it is very interesting to see, but there is a 2-dimensional Vietoris-Rips barcode there. So we are going to be able to see at some point it forms the sphere. Okay, so there will be 2-dimensional barcode. So these metric spaces can hide many topological features in them.
Sorry, why do you have this two-dimensional barcode in the 6 vertex case? So I missed my. I didn't
So
understand.
it is just so take your 6 points. It is easy to see that at scale 2, these will form. So it is not, it is just seeing what happens, okay? It is just drawing the simplex. This simplex will be born. When you add all the faces, you will get the sphere.
Is this happening in 3-dimensional real Euclidean space or 2?
So I'm just taking its geometric realization. This is a 3D picture.
Okay.
Okay, so at C6, maybe we can talk about this at the end. If you take this metric space C6 and look at its diameter 2, so VR2 C6, you will get this picture, which is exactly the sphere, or homeomorphic with a sphere. Okay.
Okay, because of this, far diagonals are more than 2.
Yes, yes. Actually, this is. So let me draw it here. Okay, so take your 6 points. Okay, so all these distances are 1. 1. Okay, now let me call this A1, A2, A3, and B1, B2, B3. B1, B2, B3. Now, when I'm drawing the 2 simplex, and note that the distance between A1, A2, and A1, A3 is 2. Okay, so if I draw this, so these edges will be added, okay, because of we are looking at distance 2. Okay, these distances are 2. So these faces are there, and if you carefully continue filling this Vietoris-Rips complex, adding the edges, you are going to add A2 to B2 and A2, B2, B1. Okay, all these edges are going to be added. So you will get the complete surface of that cylinder with 2 caps on. Okay, so
okay, thank you.
It becomes S2. So we will have a 2-dimensional interval, 2-dimensional barcode. Okay. So one way to think this about Vietoris-Rips is form the graph, fill the inside after that, or equivalently, you don't have to mention the graph. This Vietoris-Rips complex can be described directly. It is a simplicial complex whose vertex set is X, whose simplices are finite subset of X, whose diameter, which means the maximum distance between any of its 2 points, is less than R. This description and filling that degree description, graph description are coincides with each other. Okay, so, and as you can see, if we increase R, we get a bigger simplex. All simplex is there, and new simplices are going to be added, so we get a filtration. Okay, so bigger the scale, bigger the simplicial complex. So it is called Vietoris-Rips filtration. Okay, and this Vietoris-Rips filtration has many nice properties. First of all, its persistence can be efficiently computed. There are already algorithms written and actual software written for it. Okay, it is stable, and what does stable mean? It roughly means if you have similar metric spaces, then the Vietoris-Rips barcodes will be similar. In what sense? To make it more precise, you compare metric spaces by using Gromov-Hausdorff distance. You compare barcodes by using bottleneck distance. You don't have to know this. And these two differences are up the scale of 2 to each other. So metric space is close and barcodes close. And also a very important result is this Vietoris-Rips filtration captures topology very well. This is an old result, 95. Take a closed Riemannian manifold. If you look at the Vietoris-Rips filtration of it for R small enough, it will be homotopy equivalent to X. It is a huge complex. Think this is an infinite simplicial complex. You will find simplices of any dimension you want in it. It's a huge simplicial complex, but it's homotopy equivalent to X. Okay, so it means if you sample your Riemannian manifold, look at the persistent homology of it, then by stability, you will get a very good topological information about the manifold itself. And this is not the only possible result. I can think of two other results about relative to topology of the metric space X and the topology of the Vietoris-Rips filtration.
I have a question. Yeah, it might be a bit dumb question, just to have an understanding, intuition for the theorem. So let's say for some R, you find, you pick some R for which this VR complex is homotopy equivalent to X, let's say. And then you keep changing your R in one direction. At some point, you lose the homotopy equivalence and you keep moving. Can you come back to homotopy equivalence again? Does it ever happen? Or
for manifold, it cannot happen because after a while, the fundamental class will die.
Okay.
And
okay.
Maybe I'm not sure. Let me think. Fundamental class cannot be born again, but I'm not sure about it actually. So maybe somehow some other new class born, I don't know. Yeah, but for example, we know the case of S1 that does not happen. So you never come back to the original space. And actually, we have certain invariance about the points where you lose the homotopy equivalence. We are going to come to that, but I really don't know if you can ever come back to the original topology.
Okay.
Yeah.
Okay. But for S1, I think, yes, it's intuitive that there's only one kind of R. Well, I mean, there's an interval for which it works, and then you lose it.
It has S1 has a very interesting persistent barcode. It becomes homotopy equivalent to S3 at some point and S5 at some point. So it really has very interesting persistence.
Oh, really? Okay.
Yeah.
I wouldn't expect
It's not a single
that.
interval. Actually, I'm going to mention that it is not single interval. That is what you may hope at the beginning. Okay, there will be a single interval, but the Vietoris-Rips, you keep getting a third degree interval in the barcode, a fifth degree interval, and it goes on. It's really very interesting one. And we already see this in C6, as I gave you this 6-point example. When you sample 6 points from the circle, you already see there a two-dimensional barcode. Okay. So let's move on. Okay, so now we have seen an intrinsic way of getting a persistent, and that is not the only one. There are other filtrations like Czech filtration and other stuff which you can intrinsically assign filtration to metric space. Okay, it has some advantage. It is natural, intrinsic, and it lends itself to algebraic study. When I say algebra, I mean algebraic topology better, because it gives you a simplicial complex. But still, neighborhood filtration has something nice about it. Okay, it's more geometric. We see X living inside the neighborhood. It has more geometric flavor. And just to mention a situation, assume I have X and I have a sample from it, A. And then I add 1,000 more points to the sample, get a bigger sample. If my original sample is already big, the neighborhoods will not change that much. Okay, adding more samples will not affect the neighborhood that much. We are still going to get closer neighborhoods if the original sampling is dense enough. Okay? But think for the Vietoris-Rips. We know that up to homotopy, it doesn't change so much. But just thinking it as a simplicial complex, it becomes much more bigger than the original one, because we have to keep adding thousands of more simplices to the Vietoris-Rips complex for these additional points. Okay, so this shows that this neighborhood filtration has certain merits of it. And as we see in many situations, it was easy to see what's going to happen to the neighborhood filtration, while it is not that straightforward to see what is going to happen to Vietoris-Rips filtration. Okay, one question is, can we somehow find the natural embedding of X so that the persistence we get is intrinsic, although still we are using an embedding? And we are going to achieve that using injective metric spaces. Okay, so this is where the talk will be most metric. So we are going into the metric part of the talk now. So, but I'm going to describe almost everything I'm going to use. Okay, first of all, I have to introduce non-expanding maps. Those are the maps which doesn't increase the distance. Okay, so it means if you take 2 points from the domain, then compare the distances between 2 points and the distance between their images, the images should be closer to each other. Okay. So these are non-expanding maps. Another name for is one Lipschitz maps. Okay, but I think non-expanding is more geometric, so I'm going to use that. And if we take the class of metric spaces and put the morphisms as non-expanding maps, then we get a category, because composition of two non-expanding maps is still non-expanding. Okay, so we get the metric category of metric spaces, which we let us note by map. And there's one situation where non-expanding maps are important for us. I want to show it. If y equals r, then we know that the distance between images will be given by the difference between the points, difference between the values. So the non-expandingness can be written this way. Okay, if x prime is less than or equal to fx plus dxx prime. You can easily see that this will imply the other one by just sending fx to the other side. Okay, and this will be an important one. Okay, and actually, if we take infimum over x, we will get equality. Okay, if we infimize over x, and that infimum will happen when x equals to x prime, we will get equality. Okay, just plug in x equals x prime, this will vanish, and you will get equality. Okay, so this non-expanding maps has this nice structure for when the target is real numbers. Okay, so what are the injective metric spaces? Okay, since it's a topology talk, you may be familiar with injective modules. So in the category of modules, so this is very similar to that. These are the injective objects, but we had to restrict the class of certain class of morphisms. Okay, so if I take J to be class of isometric embeddings, then it is injective with respect to that class. What does it mean? Let me be more precise. Okay, if you have an isometric embedding of A into X, and if you have a non-expanding map to I, which is our injective space, okay, then you should be able to extend that map to X. So more precisely, a metric space is injective if every non-expanding map into it can be extended. Extended where? Extended to anywhere. Okay, it doesn't matter which space you get here, it can be extended. So you can find abundance of maps into our injective metric spaces. And the first example we are going to see is real numbers. Real numbers is an injective metric space, and it comes from this characterization. If you have a map from A to R, and A is a subset of X. By the way, isometric embeddings can be replaced at any time with inclusions. Okay, so most of the time I'm going to write inclusion. Then how I can expand this map? It is this one. Just take this inequality which has to be satisfied. Okay, so f tilde x should be less than or equal to this for any A in A. Take infimum. Okay, actually this is called Whitney-McShane extension. Okay, so there is a way of getting, there's a natural method of extending functions on R, and this naturality is important. We are going to use it later. Okay, so and you can just compare this way we extended f with this definition. Okay. One can show that this is actually non-expanding too. So there's a natural way to extend functions into R. Okay, a very important injective metric space, which we are going to see now, is called the Krotowski space. What is the Krotowski space? So it's underlying set. So you start with the set, any set, S, then you look at the functions from S to R. Okay. So this is the underlying set, and how you measure the distances between them, you just look at the subdistance. Okay, so take the difference of two functions and see when it gets its maximum or supremum. You can see that if S is infinite, then we can have infinite distance. That is fine. Infinite distance is not a problem. Okay, so. Or also, if you're not happy with infinite distance, there are ways to consider smaller subset of this, but I'm not going to go into them. Okay, so let us just accept that infinite distance doesn't bring any issue to us.
I have a question. So when S is finite, how does this metric space compare to the standard, the Euclidean one,
yeah,
the standard?
So it will become this then, with L infinity norm.
Oh, okay, the L infinity.
Yeah. So instead of squaring and taking the square root, just take the L infinity norm. Max xi.
Okay.
Okay. So this is not the Euclidean one, but L infinity one. L infinity distance. Okay. So this is called Krotowski space. And by the way, just a quick remark, you can show that any metric space X has closure by using the Krotowski space. You can show that Krotowski space is complete. You can embed any metric space into Krotowski space and take the closure. This is just a quick side remark for showing the completion of metric spaces, but we are not after that. Okay, so this is the Krotowski space. It is just a function space where you measure the distance of between functions by just taking the supremum of their difference. Okay. So the important thing for us is this is an injective metric space. Okay, this is one of the important points, and look how we are extending. Okay, now when we have fa to ks, be careful that any point goes to a function on S. Okay, so f tilde x s, we have to define where should f tilde x send s into. Okay, and this is exactly the extension we mentioned in the previous slide. Let me just go up a little. Okay, look at this. You use exactly the same definition. The fact that this was a natural extension helped us here to show that we can extend this function. And it is easy to show that this is really a non-expanding method if f is non-expanding. Okay. So we get a very natural extension. So the first point is Krotowski space is injective. And the second important point is we can embed every metric space naturally into Krotowski space for some x. Okay, and let me describe the map. Take x, your metric space, from the Krotowski space by using the underlying set of x, and then define this map, sending x to kx, which means every point on x should be sent to a function on x. And which function? It is just a distance function to that specific point. Send x to distance to x. Okay, and it is easy to show that it is an isometric embedding. By triangle inequality, this becomes an isometric embedding, and it is called the Krotowski embedding. So what this shows is category of metric spaces has enough injectives. So for every metric space, I can embed it into an injective space. And Krotowski is not a single one. There are many other embeddings which can precisely describe. And there's even a minimal one, which is a very interesting object in itself, which is called the injective hull, or sometimes called tight span. Okay, but injective hull is more categorical. Okay, there's even a minimal one, such that you can embed X into. But the important thing is we can always embed our metric spaces into an injective space. Okay, so what happens when we look at the neighborhood filtration here? Okay. The first thing we have shown is that the homotopy type of depth filtration is independent of the injective embedding. If you use two different injective spaces, two different embeddings of your X into injective spaces, the filtrations as a persistent family will be homotopy equivalent to each other, not just neighborhood by neighborhood, but these homotopy equivalences commute with the inclusion maps. Okay. So up to homotopy, our filtrations will be the same. Okay, and what is the idea? Idea is this: embed X into one injective metric space I, another injective metric space I prime. Then by the property of injectivity, you will get these two maps. Okay, going in both directions. Then it's still some work. You show that these two maps gives you the desired homotopy equivalence between neighborhoods. Okay. And maybe at the end, if we have time, we can discuss this. But this is the idea of proof. So you know it very naturally comes with two maps. You get very easy. The thing is showing that they give you equivalence at that level. To understand that, you have to dive a little deeper into the structure of injective spaces. And we may do that at the end.
I have a question. So the B star xi, just to recall the definition, was like a persistent complex, right?
This is
the sequence of complexes with the morphisms as R increases, right?
Exactly.
So did you define the notion of homotopy in that context?
So it actually, we didn't define, but it is very easy to define. You should have this. Thanks for asking. So, or just, I don't even need to go to this setting. So just take this, take two persistent families, YS, YT. Okay, you should have functions like this. Okay. Here are your structure maps. And this diagram should commute for all S and T up to homotopy. Okay, so.
Okay. And this is the notion of morphism in the category of X stars and Y star. Okay.
So it is just, so homotopy for individual components which commutes with the structure maps.
And in the case of homotopy equivalence, you require the vertical ones to be equivalences. Homotopy.
So this, yes, these are supposed to. So a morphism is just when this commutes up to homotopy. A homotopy equivalence is a morphism where each individual maps are homotopy equivalences.
Okay. Okay. Thank you
for asking. Okay, so we achieved our initial purpose. We get filtration, a neighborhood filtration, whose persistence is intrinsic to X. Okay, although we come to it through an implicit extrinsic way, at the end it ends up being intrinsic. It ends up being independent of the choice we started. Okay, one question. Okay, we find independence. Maybe can we find a way to intrinsically define that homotopy? Okay. And that is the second result. Yes, there is. Actually, that filtration, whenever you have injective embedding and looking at the neighborhood filtration, it is homotopy equivalent to the Vietoris-Rips scaled by 2. Okay, so we are turning back to Vietoris-Rips again. This filtration, which we get in a quite geometric way, ends up being homotopy equivalent to Vietoris-Rips. Okay, so we build a bridge. I interpret it as building a bridge between the algebraic and geometric analysis of metric spaces or metric data, if you think data analytic way, which means like you have samples and noise and stuff. Okay, so this builds a bridge between these two worlds. This is quite geometric, but initially you thought it will not be computable because think about the Krotowski space. It's a huge space. How are you going to look at the neighborhoods and compute the homology there? So it seems theoretically very nice, but computationally hopeless. While Vietoris-Rips is computationally very efficient. You can easily compute Vietoris-Rips family and its barcodes. So these two end up being same. In the remaining part, let me talk about some applications. And we can, after this is the main core of the paper, and we can stop anytime after this point. And how, until when I should go on? I cannot hear you.
So the time is an hour. So, but yeah, so we started at 3:30 until 4:30, but it should be okay. You can either count the time, including the questions, or without. So either,
Okay, so
either
let
way
me
is
just
fine.
mention at least one or two applications of this idea.
Yeah, just don't rush.
Okay, so one thing we are going to get easily from this approach is persistent QNet. QNet theorem for persistent modules. Okay, so we have to take, to be able to talk about QNet, we have to take the tensor product of two persistent modules, right? And if you do that and look at the barcodes, you are going to see that the resulting barcodes can be obtained this way. Okay, so take the interval from the first barcode of dimension m, take another interval from dimension n from the other barcode, look at the intersection, and that intersection will be one of the intervals of the sum of the dimensions. Okay, this is how barcodes come together in the case of the tensor product of persistent modules. Okay, and what about the tensor product of metric spaces? It is defined in a very natural way. So you define the resulting metric as maximum of individual metrics. There are other ways to define product metrics, but this is the most natural one. Okay, and several people several times proved QNet formula. Okay, and also I did in another paper using just the simplicial ideas. If you look at the Vietoris-Rips complex of the product, then you can show that the barcode comes from the product. So it is exactly the persistent version of the QNet. Okay, and all proofs I have seen proceeds in the simplicial manner. Okay, and it is a certain combinatorial argument. Now, using our idea, we are going to get a very direct geometric proof. Okay, so take I and I prime, two embeddings of x and y, then you can show that I times I prime is also injective. And if you look at the neighborhood of it, neighborhood of x times y in I times I prime, you will exactly get the product of individual neighborhoods. Okay, then you just apply standard QNet and you will get persistence you want. Okay, so this is one application. And another application, this is more on the geometric side. Okay, so in this application, we were able to bring the geometric side to the help of the algebraic side. But we can also go the opposite way. So the filling radius of a Riemannian manifold is defined by Gromov in '83. And it is already an important object in the study of manifolds, Riemannian manifolds. Okay, it is defined this way. You embed X into the Grotowski space and see when the fundamental class of the manifold X dies. Okay, that is called the exact time when the essential fundamental class dies is called the filling radius. And then through our way, we can show that there's a barcode in the Vietoris-Rips filtration of X. With this side, this extra factor 2 is coming from the fact that the neighborhood and Vietoris-Rips filtration are related up to scale 2. Okay, so this 2 is coming from that. So there will be a barcode in there will be interval in the top dimensional barcode of Vietoris-Rips. And actually that will be the only interval in there whose left point is 0. So we can. Yeah.
Is K supposed to be n here or?
Yes, it's supposed to be n. Thank you. It is the top dimension of the. It is the dimension of the manifold. So now we can get the filling radius using the Vietoris-Rips. There's a unique interval corresponding to that. Only interval in dimension n with left endpoint 0. And for example, we can get upper bounds to filling radius through that. So a spread is a generalization of the radius of a metric space. You just look at a space in subspace in X whose diameter is less than R and whose distance to the whole outer space is less than R. That's called the spread of X. And then, for example, we can show this spread bounds the Vietoris-Rips through simplicial arguments. As a result, spread has to bound filling radius. Okay, so now we can bring tools from the Vietoris-Rips, tools which or results which Vietoris-Rips gives us very easily, and apply it to this geometric setting to find bounds for this geometric quantity. Okay, and I think I can stop at this point, and I will be happy to take your questions if you have any.
Okay, thank you very much, Osman. So any questions for Osman on install? Okay, so well, I have a question. So maybe it's like a question whether we can ask it or not. So in this context, can we also ask the Meyer-Vietoris sequence? I think it's problematic for these kind of complexes, right? That doesn't really. So does it really help? The embedding approach, does it really help there?
So it is more in the relative homology setting, right? So to be able to get some results in that direction, we need to consider, I think, relative persistent homology, which is something actually I am planning to keep thinking about, but I have not studied yet. So I think if we define somehow the relative persistent homology, then I think what comes out of Meyer-Vietoris theory.
Yeah, I think I'm thinking more simply in terms of clique complexes and two subcomplex, and in that sense, you know, you can look at the homotopy fiber.
I see. So actually, I will not be able to comment about it. I don't know how it is going to work in this case.
Okay, yeah, I was just curious if there's a connection, but the result about the QNet is really cool. Yeah,
it is very nice, straightforward geometric way of showing it. So it's not the first time someone shows it, but so it shows that we can bring the results from algebraic topology directly, because some geometric structures will be reflected in the neighborhood. So this shouldn't be the only way. Yeah, there should be other ways to bring the geometric structure into Vietoris-Rips through neighborhoods.
Okay, so
I have a question.
Okay, yeah, there's a question.
So when you for your proof in getting the homotopy equivalence for the Vietoris-Rips and metric spaces, I suppose you also have a naturality in X, because at least it plays off nicely with the projection maps for Tunis. Is it natural with all types of maps in your category J, or?
So for the how we get the homotopy equivalence between Vietoris-Rips and this neighborhood filtration is actually using the nerve theorem and the naturality of map coming out of nerve theorem. And for your second question about, so when I define injective spaces, we have to use these inclusions, right? So are you asking that what if I use a more general class instead of these isometric embeddings?
No, I'm just, how should I'm asking whether your homotopy equivalence is natural in X, really. When you consider a map from X to Y, do your homotopy equivalences between the Vietoris-Rips and the neighborhood complexes also commute with the maps induced between each?
Yeah, I see. I think for the we didn't get in that result at this Vietoris-Rips level. We get the neutrality in the neighborhood level. Okay, so we have homotopy equivalence here. Okay, or
Oh,
But I
do we
think
have
it
the
should be workable.
same I in for X and Y, or
So
can it be different?
like I was thinking, yeah, maybe it is better to say. So like more natural I said is this: if you have this map, it's not going to be equivalent, but you will just get a map. You will just get an induced map. I prime. Okay, there's this naturality in this sense. We can naturally extend that map between the embeddings. But I believe we should be able to get it even this sense. But the proof of that statement is quite technical.
I see.
And we didn't go over after it. But I believe it should happen. The thing is, you have to use nerve lemma, and again, you have to use the naturality of nerve theorem in this setting.
Oh. So what does this scale of 2 come from? Is it easy to see, let's say, in a simple example like a circle or something?
Okay, so let us take these 2 points. Okay, look at the Vietoris-Rips. Let us say distance 1. Okay. Exactly at 1, you will get the interval, right? Or when you just epsilon exceed 1. Okay, so everything will die at that level. Okay, so we know that in this setting, the homology dies at level 1, just 0-dimensional homology. Let us think with the injective setting. So you can take the interval, okay, and show that this is injective. Okay, interval is injective, and embed your endpoints here. Now at here, exactly at 1/2, the homology will die.
Again, we are using that metric that that's the infinity, right? We cannot. Yeah. We're not using the Euclidean. Can we use
but
the
this
Euclidean?
is in 1 dimension. They are same.
Oh yeah. Okay, that's right. Okay. But in general, the Euclidean one is not injective. You're saying.
In general, Euclidean one is not injective. No. Only at dimension 1. One can show that Euclidean one is not injective. R2 is not injective. You can show this. Take this metric space. Okay, 1, 2, 1, for example. Okay, so this 3, so this is 2, 3, 3. This 3-point metric space can be embedded into R2 with Euclidean, but that 4-point metric space cannot be embedded. This cannot be embedded into Euclidean. You cannot find the distance in the Euclidean plane such that these distances are realized for the triangle.
Mm-hmm. Okay. Yeah, I think that gives some intuition. Thank you. Okay.
Can I also ask a question?
Sure.
In this category of metric spaces, your morphisms are now growing.
Yes.
So is this a standard integer or is it like a special category?
So this is the standard metric category. You can define other categories by just Lipschitz maps. Okay, this is the standard one, but we can also define, we can take our morphisms as this. There exists a Lipschitz constant C such that fx, so distance doesn't grow more than C. And composition of 2 such maps are again a Lipschitz map. So this category can be taught, but this is the most, I think, most well-behaving one.
One more question is that you look at injective objects, and so there's no abelian category here. Right? You can't talk about projectives or etc. But is there a way to include homological artifacts?
I don't think so. Do you? I don't think we have a nice direct sum operation in metric category. We have product, but I don't think we have sum. Or it may be not well behaving metrically. maybe if you put infinite distance between the components, you can talk about direct sum. But I've never seen anyone trying to do homological algebra or something like that in geometric category.
Thanks.
Okay, any other questions?
I think Akif has a question. He was
Okay.
raising hand.
Hi.
Okay.
So,
Hi, Akif.
hi. I'm going to ask if, for example, if you change the category, like deal with lower metric spaces, the category is enriched over the 0 to infinity, the monadal poset. I mean, a similar, can we build a similar theory which works, for example, better with homological algebra, constructions, etc.?
I don't know that setting actually. So how I don't know how that enriched category is defined. There may be, yes, but unfortunately I'm not aware.
It is, maybe I cannot use the chat, but anyway,
Yeah,
okay.
You can.
Actually, I think the Kuratowski embedding you mentioned looks very much like a Yoneda embedding. So I would suspect there is a way to make what Akif say work.
Okay. Yeah, thank you.
Yes. And by the way, there are other more geometric descriptions of injectivity. I preferred here giving the categorical one because I thought people may be more inclined to, or that will be easier for them because you are topologist or you are topologist here. It will be easier to describe that way. But there are other more geometric ways of describing the injective metric spaces. The geometry way will be this: if you take any collection of balls which pairwise intersect, then they should have a common intersection. For example, this will be other way of defining injective metric spaces, and one can show that this is equivalent. It's not straightforward, but you can show that this is equivalent to having this injectivity property.
Okay, sounds good. So maybe it's time to close the session. So let's thank Osman again for this very nice talk. Okay, thank you very much, Osman.
Thank you.
Thanks, Osman.